Now we'll take the question. Find all the points of discontinuity of greatest integer function. Means at what points this greatest integer function is discontinuous, we have to make a list of those points. And now in order to be more clear, let me write the graph of this greatest integer function. To plot the graph, we know already greatest integer of x will be 0 if x equal to 0. When x is 0, greatest integer of 0 is 0. When x is greater than 0, maybe between 0 and 1, greatest integer of 0.1, greatest integer of 0.2, greatest integer of 0.99, greatest integer of 0.999, all of them will be equal to 0. But when it takes 1, greatest integer of 1 is again 1. So let me write for what values of x greatest integer function will give us 1. Yes, x greater than or equal to 1, strictly less than 2. Now greatest integer of x is equal to 2 if x equal to 2 or greater than 2 and less than 3. Now for what values of x greatest integer of x will be equal to -1 if x greater than or equal to -1, it is less than 0. Like this it continues. This is enough information to write the graph of greatest integer function. Okay, now let me take one by one. Greatest integer of x is 0 for all values of x lies in this interval, greater than or equal to 0, strictly less than 1. So strictly less than 1, not equal to 1. Here let me write not. We are not taken x equal to 1. When x is 0, greatest integer function will give us 0. When x is 0.1, greatest integer function will give us 0. When x is 0.2, greatest integer function will give us 0. Like this it goes up to 0.999. But when x equal to 1, it becomes 1. Here I darken this circle, indicating when x equal to 1, the function value is 1. And this value of function will be 1 whenever the values of x greater than 1, strictly less than 2. And here I write a not without shading, indicating at x equal to 2, the function value becomes 2. So the values of the function will be 2 whenever x value is greater than or equal to 2, strictly less than 3. Similarly here, when x equal to -1, the function value is -1. I have to shade this. And the values of the function will be -1 whenever the value of x is greater than -1, less than 0. So here at -1, there is a gap. Like this it continues. So this is what the nature of graph of greatest integer function. By looking at this, it is very clear that it is discontinuous at many points. What are the points at which it is discontinuous? Look at here, at x equal to 1, at x equal to 0, at x equal to minus 1, at x equal to 2, at x equal to 3. What kind of numbers these are? Minus 1, 0, 1, 2, 3. So it is integers. So we can say by looking at the graph, greatest integer function is discontinuous at all integral points. That is what we decide with the help of graph. Now let me check using the definition limit of f of x as x tends to a equal to f of a. For instance, let me take real number c equal to 1. Or at 1.5, let c be a real number such that r, which is not equal to any integer. For instance, let me take c equal to 1.5. Clearly 1.5 is a real number but not an integer. At this point, this function is continuous. Look at here. Around the point 1.5, is there any break in the curve? No break in the curve. So it must be a continuous at this point. Let me check. Let c equal to 1.5. Now let me find out LHL. A limit of f of x as x approaches to 1.5 from left side. This is the limit as x approaches to 1.5 from left side. What is f of x? Greatest integer function. This is f of x. Now this is equal to greatest integer of 1.5. What is greatest integer of 1.5? It lies in this interval. It is equal to 1. Now find out, because as x approaches to 1.5, here it is 1.5. Now x is approaching to 1.5 from left side, means maybe it is a 1.49. Still it lies in this interval, so greatest integer of that number is equal to 1. Now right hand limit, a limit as x approaches to 1.5 from right side, limit as x approaches to 1.5 from right side of greatest integer of x. This is 1.5. What is greatest integer of 1.5? It is equal to 1, because whenever x approaches to 1.5 from right side, through the value is slightly greater than 1.5, maybe 1.5001. What is the greatest integer of 1.5001? It is equal to 1 only, because it lies in this interval. So LHL equal to RHL. Therefore, limit of f of x as x tends to 1.5 is equal to 1. Limiting value exists. And function value at 1.5, it is greatest integer of 1.5 is equal to what? 1. So function value, limiting value are identical, they coincide. Therefore, we can write since the limit of f of x as x approaches to 1.5 same as function value at 1.5, f of x is continuous at x equal to 1.5. Now similarly, you can take any other number, any other real number which is not an integer, maybe 1.6 or maybe minus 1.5 or maybe 0.1 at any non-integral point you take, you are going to get limiting value equal to function value. Now let me generalize this. Let C be any real number which is not equal to any integer as x approaches to C from left side, as x approaches to C from left side of greatest integer of x, as x approaches to C from left side, it is greatest integer of C. Suppose if C value is 1.5, greatest integer of 1.5 is 1. Since C value is not defined, it is a real number which is not exactly an integer. So by knowing that, we can write the result. You keep it as greatest integer of C. Now RHL, a limit of f of x as x tends to C from right side, greatest integer of x as x approaches to C from right side, it is greatest integer of C. Both will be same. LHL equal to RHL. Therefore, limit of f of x as x tends to C is equal to greatest integer of C. Now, what is the function value at C? Just like function value at 1.5. So, it is greatest integer of C. So, the limit of f of x as x tends to C is equal to function value at C. Therefore, f of x is continuous at x equal to C. That is, at all real numbers other than integer. Or f of x is continuous at all non-integral points, you can write. At all non-integral points. That is, at all non-integral points. Now let me take the other case. Let C be an integer. Let me take C equal to 1. Now what happens? As x approaches to 1 from left side, what is the greatest integer of this number? A number which is slightly less than 1. It is approaching to 1 from left side, maybe 0.999. Maybe 0.999. How much you are going to get? 0.999 lies in this interval. Its value is 0. Now, as x approaches to 1 from right side, whenever x is approaching to 1 from right side, the value of x is slightly greater than 1, maybe 1.001. In this interval it lies. Greatest integer of 1.001 is what? 1. So LHL not equal to RHL. Therefore, limit of f of x as x tends to 1, it does not exist. Therefore, f of x is discontinuous at x equal to 1. I hope you followed this. Now, if I take 2 also, as x approaches to 2 from left side, the value of x will be slightly less than 2, maybe 1.999. Greatest integer of 1.999 will be equal to what? In that case, LHL will be equal to 1. RHL as x approaches to 2 from right side, slightly greater than 2, maybe 2.001. Greatest integer of 2.001 is what? 2. Like this, it fails to be continuous at all the integral points. So now let me generalize this. Let C be an integer now. As x approaches to C from left side, now here instead of C, what I do, I write C minus R. What these are? Small positive number. Small positive real number. Like when C is 1, it is a 0.001, then it will become 0.999, something like that. Then what is the result you are going to get? 1 less than the value of C. As x approaches to 1 from left side, what is the limiting value we are going to get? 0. If x approaches to 2 from left side, greatest integer will give us 1. 1 less than the integer what we are taken. So that is what I indicated here. RHL now. Look at here. When I take 1, it becomes 1. RHL. LHL becomes 0. So indicate that I am written that. Now x approaches to C from right side. X approaches to C from right side. Here I had to write slightly greater than R. For that I had to add some small positive real number. For 2, maybe 0.01 I added. Greatest integer of 2.01 is what? 2. So therefore here I am going to get C. So LHL different from RHL. So limit of f of x as extends to C does not exist. Therefore f of x is discontinuous at x equal to C. But what C represent? An integer. Therefore f of x is discontinuous at all integral points. So what was the question? Find the points of discontinuity of greatest integer function. What are the points of discontinuities now? The integral point. So you should remember, greatest integer function fails to be continuous at all integral point and it is continuous at all non-integral points. Now finally we will take the theorems associated with this continuity. Okay, now we will discuss some of the important theorems associated with this continuity. The first theorem says f and g are two continuous functions at C, two different functions, but continuous at a same real point. Maybe at x equal to 1, f is continuous, g is continuous. Then their sum of two function is also continuous at the same point. Their difference of functions is also continuous. Their product of functions is also continuous. As well, the quotient of those two functions is continuous provided the denominator function should be different from 0 at that particular point. As an example, suppose if I take f of x equal to sin x and g of x equal to say x square. It is well known fact, sin x, by that graph we can say that it is clearly continuous. What about x square? Yes, it is a parabola opening upward, no break in the curve. It is a continuous. Or else, with the help of one of the example, we already proved that every polynomial function is a continuous function. So it is a polynomial. Therefore, it must be a continuous function. So I have taken two continuous functions. Let me take a specific point. Say at x equal to 1. Of course, these two functions are continuous at all real points. I have taken one particular point, that is 1. That is C. C value is 1. Now, as sin x and x square are continuous at x equal to 1, their sum of function, that is Sin x plus x square is continuous at x equal to 1. Their difference of function, that is f of x minus g of x, sin x minus x square is continuous at x equal to 1. Then their product of function, it is f of x into g of x, it is a sin x into x square is continuous at x equal to 1. F divided by g, that is quotient of function f of x by g of x, sin x divided by x square is continuous at x equal to 1, provided the denominator function is different from 0 at that point. Is this second function g will become 0 at x equal to 1? No, therefore it is a continuous function at x equal to 1. Like this, suppose if I change the value of c as 0, clearly sin x and x square both are continuous because graph of sin x, it is continuous at x equal to 0. Graph of x square, yes, it is continuous at x equal to 0, no break in the curve. Therefore their sum is continuous at x equal to 0. The difference of function continuous at x equal to 0. Their product of function continuous at x equal to 0. Now their quotient of functions, sin x by x square, is it continuous at 0? No, it is not, because the denominator function at that particular point should be different from 0. Why? What is the reason behind that? Suppose if the denominator becomes 0, the ratio is not defined, means f by g of c is not defined. If the function value does not exist, then it cannot be a continuous function. I hope you followed the property. With this property, we can write two more statements. But with the help of these properties only, we are able to write. If f is continuous, minus f is also continuous. If sin x is continuous, minus sin x is also continuous. If x square is continuous, then minus x square is also continuous. That is what the property says. This is y equal to x square, isn't it? You write the graph of y equal to minus x square. How it will be? It will be like this, minus of x square. It is also continuous one. That is what the property says. How we are able to get it? By using this. I take g as a constant function. G of x equal to minus 1 I take. Then f of x is as it is, g of x is minus 1. Their product of function is also continuous. So f of x into minus 1, that is minus of f of x is also continuous. In the same way, if a function is continuous, its reciprocal is also continuous, provided the denominator function should be different from 0. That is, f is a function, that is the sin x is a continuous function, then 1 by sin x is also continuous. At which points it is? The points leaving where this sin x becomes 0. So x should be different from n pi. Leaving these points, 1 by sin x is also continuous. How are you able to get it? F of x by g of x is continuous. So when I take f is equal to 1, then I becomes 1 divided by g of x is continuous. So instead of taking g, I written here f. So if f is continuous, 1 by f is also continuous, provided that at that particular point the function should be different from 0. Next, every rational function is continuous one. What is a rational function? A rational function is of the form p of x by q of x, where p and q are polynomial functions, where pq are polynomial functions. Now let me take an example. Say it is x plus 1 divided by x square plus 1. Clearly this is a continuous function. How are you able to say this? I take the numerator as f of x, denominator as g of x. Numerator polynomial, denominator polynomial. We know that every polynomial function is continuous at all real points. So x plus 1 is continuous, x square plus 1 is continuous. If f and g are continuous, just now we said f by g is also continuous. As two polynomials are continuous, their quotient of polynomials, nothing but rational function, must also continuous, provided this is different from 0. In this case, x square plus 1 never becomes 0, therefore clearly it becomes a continuous. Suppose if you have x minus 1, of course it is continuous except at only one point, because this function is not defined when x equal to 1. So that is what we can say this. Every rational function is continuous. Next, suppose theorem 2 says, suppose f and g are real valued functions. What is meant by real valued function? In first PUC you already come across this. What is a real valued function? There are two types of function. One is real function, another is real valued. In order to say that f is a function from a to b, to say that it is a real function, both a and b must be either real set or subset of real set. Then only we say that it is a real function. Real valued function means no restriction for domain, but codomain should be either it is real set or subset of real set. That is what a real valued function. Now, f and g are real valued functions such that f naught g is defined, that is composition of two functions. This is also we learnt already in the first chapter. Composition of function is defined at point C. If g is continuous at C, f is continuous at g of C, then f naught g is continuous at C. Let me write point by point. F naught g of C exists, is defined F naught g at C is defined, means it must be a finite real number. If g is continuous at x equal to C, and f is continuous not at C, at g of C. If these three conditions are satisfied, then we can say f naught g is continuous at x equal to C. Okay, now let me take an example. Say I take hx equal to sine of x square. We'll check whether it is continuous at x equal to 0 or not. Means the C value is 0. For that I had to check these three conditions. Whether f naught g of 0 is defined or not. Now I had to split this as f of x equal to sine x. G of x equal to x square. Now check what f composition g of x will give us. It is f of g of x. It is f of x square. What f of x? Sine x. What f of x square? Sine of x square. Now it is a composition of functions. To check whether composition of function is continuous at a point C or not, this theorem is going to helpful. How to check this? First, that composition of function at the given point must be well defined. Let me check the first point. F naught g of 0, it is f of, that is the sine of 0 square, it is a sine 0, 0, it is a defined, a value is defined. First one is cleared. G is continuous at C, here it is G. G is continuous at C equal to 0. What is G? X square, parabola, it is continuous at 0. Next, F is continuous at G of C. F is continuous at G of C, that is at G of 0. What is G of 0? 0. That is, what is F? Sin x. Sin x is continuous at x equal to 0. All the three conditions satisfied. F naught g is defined at C. G is continuous at C. F is continuous at G of C. Here I have taken C as 0. My job is to check whether sine of x square is continuous at 0 or not. For that, whether G naught F is defined, F naught G is defined at 0 or not. Yes, it is defined. We are getting a finite real number. Whether G is continuous at 0. Yes, what is the function G be defined? X square. Clearly x square is continuous. Then I had to check whether this function F is continuous at G of C. G of C is G of 0. G of 0 is 0. Whether sin x is continuous at 0 or not. Yes, it is continuous. No break in the sine curve at 0. So, all the three conditions satisfied. By this now what I can conclude? Therefore, this function hx, nothing but what it is? F naught g. I define this given function as composition of two functions. In order to find whether this function is continuous or not, I am taken the help of theorem 2. So, f naught g of x and hence sine of x square. Therefore, sine of x square is continuous at x equal to 0. So, this is how we have to prove with the help of theorem. Similarly, the other functions also we can answer. In fact, this question, this kind of questions, once in the board exam they asked for 4 marks. Very simple. In order to say that composition of two function is continuous means at a point C, basically function value at C must be defined and the inner function G must be continuous at C and F is continuous at G of C. If these three conditions satisfied, with the help of theorem we can say that F composition G is also continuous. We can make use that theorem to answer this kind of questions. I hope it is clear. In the textbook one more example they are given, in fact. You please note down that example also. Now, with the discussion of all these points about continuity, we are now ready to answer the questions given in the exercise. So, please make an attempt to answer those questions. In the next class, I will be answering those questions. Thank you.